Okay. Hi, everyone. I assume the people in Zoom cannot hear me, but they can hear me. Well, okay. So we're about to start. I'm terribly sorry for the technical delay. It seems that the sort of equipment's changed a little bit here with a sort of recent event. Yeah. Enrique was sort of due to present Javier, but unfortunately we can't hear him through Zoom. So I'm going to give. So I'm gonna start the seminar. Yeah. We're gonna start. We're gonna start the seminar because the introduction will not come through Zoom. So I'm gonna hand straight over to Javier for you to start the seminar. So Dr. Javier González Payo has visited us from the Universidad de Complutense in Madrid, and he's going to talk today about search and characterization for multiple host star systems. So thank you very much, Javier.
Okay, buenos días. I'm going to talk in English. Sorry about my rusty English. But okay, I didn't practice in a lot of time. Okay, thank you for coming for this presentation that is in the framework of this 20th anniversary of the Spanish Virtual Observatory. I'm going to present part of work that is developed inside my PhD thesis. Okay, first of all, I'm going to introduce myself. My name is Javier González Payo. Many of you don't know me. My background is of engineering. I worked during the most of my professional life into engineering, in particular in telecommunications, mobile, and voice over IP networks. I did my BSc and my SSc in telecom engineering in Universidad Politécnica de Madrid. After I got my PhD in engineering in Universidad de Vigo, and some years later I decided to start one of my illusions, one of my things that I always decided to be is the astrophysics. So I decided to start the MSc in astrophysics in Universidad Complutense de Madrid, and after I decided to start my PhD. So now I'm finishing my PhD. In fact, it's finished. I'm just waiting for the defense date. And the work I'm going to present is one of the papers that were published inside the framework of my PhD thesis. Okay, many of you don't know what is stellar multiplicity. So what is stellar multiplicity? Is when two or more stars are gravitationally bound and they are orbiting each other, like in the small video that you can see into the slide. And it's a phenomenon that is very common in the universe. In fact, more than 50% of the stars in the universe are multiple or have a companion, at least one companion. And we know that the more massive the star is more probable that this star have one or more companions. In the opposite side, smaller stars, for example, red dwarfs, normally are more isolated. So the multiplicity fraction of this type of star is very low. It can be around 3, 4, 5%. And stellar multiplicity is not only something that is exotic, that can be interesting, is very important for astrophysics. They help to measure many things, for example, the stellar masses. And this measurement of the masses is very important to understand how is the evolution of stars, how they are born and how they finally die. And of course, they offer clues about the formation of the stars. Sometimes it's interesting to know why the stars forms in groups Sometimes they drift away alone. So stellar multiplicity is really important. There are many types of multiplicity star systems. A first classification can be in the number of companions, can be multiple star with only 2 stars, a binary star, or a hierarchical. A binary star are 2 stars that orbit each other, just 2 stars orbiting each other. There are many types of classification, many types of multiple or binary stars. For example, optical or visual, that is not the same. Optical or visual binary stars are the stars that are detected by naked eye or by through a telescope, small or big telescope. Is when we see in the projection of the stars from the celestial sphere, we can see 2 stars that are very close together. But it doesn't indicate if it is binary or not, because due to its projection on the celestial sphere, we can think that one star is very close to us, relatively close, and the other one is very far away. But we look at them and we can think that they are together. This is the typical optical binary, that they are close in the sky, but they are really very separated, very far each other. They are not gravitationally bound each other. Other one is visual. Visual is the same, but they are really at more or less the same distance. So probably they are gravitationally bound. There are other types, for example, eclipsing, that is when the rotation is in a plane that is perpendicular to our vision. So sometimes one of the stars pass through the other star and eclipse the light from the farthest star. And the other type is hierarchical. We can see cases in our galaxy with up to 7 or even more companions. Normally they are hierarchical, they are in different tiers. So the most typical is, for example, a binary star that is rotating another binary star. So they have different tiers, different steps into the hierarchy. Some interesting things, some fun facts for us, people that normally doesn't think about stellar multiplicity, is that one of the most famous star in the sky, that is Sirius, that is the brightest star in the night sky, is a binary system. It's composed of 2 stars, Sirius A and Sirius B. Another case is our nearest neighbor, Alpha Centauri. Alpha Centauri is just 1 parsec away from us. 1 parsec is about 4 light years. And curiously, is a triple star. As you can see in this short video, is composed of 3 stars. The 2 biggest one are Alpha Centauri A and Alpha Centauri B. And another star, a little bit smaller, that is called Proxima Centauri, that is the closest star to the Sun. Okay, I would like to talk about the history of multiple star astronomy. Probably it's an issue that is not very studied during the study of astrophysics or astronomy in general, but one of the articles that we published inside my PhD thesis, it was related to a case of archaeoastronomy. And I think it's very interesting for people that is concerned about double star astronomy. Even though the multiple astronomy, the multiple star were studied from a long time ago, from ancient times, nobody gave any type of importance about this fact. In 1616, Benedetto Castelli, an Italian astronomer, asked to Galileo for observing two stars that they thought they can be a double star. So Galileo observed, and finally they concluded that Mizar A and B was a binary system. 1 year later, Galileo, by himself, discovered or observed the trapezium. Trapezium is a group of 4 stars inside Orion, and it's theta 1 Orionis A, B, and C. Some years later, another astronomer discovered the D star because it was formed by four stars. Some years later, Martinus Hortensius and Giovanni Battista Riccioli found 2 more binary stars. Later, Robert Hooke with Versa team. After 2 Jesuit fathers, Catholics, French, Father Jean de Fontenay and Father Jean Richaud, discovered 2 more binary stars that are Equus and Alpha Centauri from the South Hemisphere. But the first official list in history about binary stars was performed by Christian Mayer, that published a list with 72 double stars. It started a passion to discover new binary stars and to try to publish new lists. So in 1782, William Herschel published another list in the company of his sister Caroline. He's not so famous, and published a list of 269 double stars. Later, they published another 2 more lists about double stars. That's the official history. But we discovered that there was old astronomer, a Sicilian astronomer, that in 1654 discovered or published a list of 12 double stars, that it was much earlier than the first official list from Christian Mayer, in particular more than 100 years. So our work was performed to try to find out if these stars were really double or binary stars. For that, we obtained it with his book, written in Latin, the Systemata Orbiscum Etici, in a small section, not studied, never studied, incredibly nobody studied, with a total of 12 stars. For 5 stars, Odierna gave us a description, an approximate separation, and some ancient coordinates. For 3 stars, only description and approximate separation, and for 4 stars, just the description. The description is simple description in Latin, trying to explain or trying to give instructions to normal people without any type of knowledge in astronomy to try to locate the star inside its constellation. I put here an example. Secunda Spondylii Scorpionis. It was the description of that star. So in our case, we try to obtain an image of the old constellation, Scorpio, and we focused on the second vertebra of the Scorpionis that it was Odierna provided. So finally, we discovered that it was Zeta 2 Scorpionis. Okay, it was okay, but sometimes we don't have enough information. So we have to change our mind to try to put into the Odierna's shoes, trying to see how can I think a person from the 17th century. So in the case of, we have the ancient coordinates, we transformed it to ecliptic coordinates, and the ecliptic coordinates were transformed to J2000 through a web page with a converter in a web page from NASA to try to obtain these modern coordinates. Anyway, we can think that the position during the 17th century of a star is not the same in the 17th century that now, because there is a movement that is the equinox precession movement. So we try to compensate. We discovered that from 1654 until up to date, the equinox precession was about 4.8 degrees. For the stars, we have the coordinates, the 5 stars. We obtained that the mean of the 5 identified stars, it was more or less 4.8 degrees. So we were in the right way. In any case, we discovered the 12 stars. This is the table of the left side. They appear with different colors. Green are visual binaries, so they are bound, gravitationally bound. And in red, they are visual binaries, so they are very close together, but really they are not bound. That it was impossible to determine from Jodierna in the 17th century. There was some cases that there was 2 companions instead of 1. For example, the pair number 12 that is composing the trapezium, and Jodierna only indicated that there was a companion, but didn't say anything about the other one. We noted all of them. In orange, for example, the pair number 2 is in Epsilon Tauri. We discovered that there are no companions. If you see the pictures in the right side, in the number 2, the star Epsilon Tauri Ein is completely isolated. The reason, maybe a glare inside his telescope, maybe a phenomenon in the sky like a nova or supernova, maybe the pass of an asteroid, a planetoid. In any case, we don't have enough information because we don't know exactly the date of the observation. Because the book was published in 1654, but we don't know exactly the date of the observation. So we preferred to leave this pair as not identified. Okay, leaving apart the history of astronomy, we continue about some concepts related to multiple astronomy, multiple stars. There are different methods to try to detect companions for stars. 3 types of methods: direct imaging, spectrometric methods, or astrometric methods. For direct imaging, there are many types of methods. One of them is optical imaging, is just observing through naked eye or through a telescope if there are 2 stars that are close together. Another one is coronography. Coronography is a simple method to hide one of the stars, normally the brightest star, to try to hide the light that is probably hiding the light of other dimmer star to try to see what is the companion. This method is used also not only for discovering new companions, but also for discovering new exoplanets. Lucky imaging is like the picture at the bottom. Lucky imaging, due to the disturbation into the atmosphere, if we take a picture with a long exposure, we can obtain all the noise that is provoked by this noise in the atmosphere. So the lucky imaging consists of setting or taking a lot of short exposure pictures, and as the number says, sometimes we have luck. We are lucky to find one image that is better than the rest of them with less perturbation. More or less, probably the method is more complex, but more or less to take an idea about this method. Another family of methods is spectrometric methods. So they are a type of binary system that is called spectroscopy binary. We can detect, due to it's impossible to distinguish the light because they are very close together, and because they are very brilliant, very brightful, and we are not able to distinguish both stars. So if we obtain spectra, different spectra in different dates, we can see a shift of a line, for example, hydrogen, until up to blue or to the red, and we can guess that probably there are two stars that are rotating, and when the star is approaching in that moment in this orbit, approaching to us, we can obtain this line in blue, and when it's going further, we can obtain the red because it's looking further than us. For my PhD thesis and for the virtual observatory tools I've used, I prefer to use the astrometric methods because they were more interesting for me. That it was the idea. The target is to find the same proper motion and to have same parallax. What's the idea is that if we have two stars and they are moving together, they have proper motion, similar proper motion, is the velocity that they are displacing or moving through the sky, through the celestial sphere. And similar parallax, because parallax indicates the distance. So if they are in the more or less in the same distance with some margins, we can understand that if they have also similar proper motion, they are together. They are moving together, so probably they are gravitationally bound. This is the idea. We tried to collect how many works about multiple systems with planets were performed in the last 20 years. And we found more than 2 dozens of works. I prefer to put here the best because the sample it was big enough to be considered with accuracy. So there was a work up to 50 parsec of distance from the sun, another one 25, another one 200, and two more works with 500 parsec. These are the most interesting works. In our case, we prefer to put a limit of 100 parsec and to handle this sample. Why? The reason is because the sample we had with 100 parsec is very complete. It's also studied by other authors, and because it was the first time that we were going to use Gaia DR4. Sorry, the Gaia DR3. Gaia DR3 is providing very accurate astrometric data. So probably the data would be more accurate than the rest of the works. Other authors say, for example, Relais, collaborators in 2021, she measured a multiplicity fraction of 27.4%, but depending on the spectral time, this is a good data, a good result. But other studies provide sometimes inconsistent results about relationship between stellar multiplicity and the properties of the planets itself. Our work is performed at this distance with an extended example because it was composed of 212 multiple stars plus 687 single stars, and using Gaia DR3 to improve our completeness of the sun. There are many virtual observatory tools, you know, more than 20, more than 30, but in my PhD, in particular in this work, I tried to focus on these 4 tools that for me were very important. First one, Aladdin Sky Atlas, that provides information, especially visual, that is the feature that I prefer to use, Aladdin Sky Atlas, because with the other tools I'm obtaining a lot of data, but I prefer to see by my own eyes what is the position, how much separated they are. So Aladdin is very nice to check very well what are the distance, the separation between stars. Sinbad that provide one thing that for me is very important, that is a unique name, the name, because a star can be called in different names, many names, depending on the catalog that this star appears. And I prefer to use only one name. So Sinbad provides me the main name, and I use it to use the main name. Also is a base to obtain what are the main papers related to the object that we are studying. This year, that is a portal web page where we can connect with different catalogs, with different databases, and obtain different data. And to obtain those data, we use Topcat that connects with all type of databases. In particular, the utility that table access protocol query that is very used, especially for me, using some lines of code programmed in ADQL, in Astronomic Data Query Language, that it's perfect to establish a type of conditions and to obtain the possible companions related to the star we are trying to study. For example, in this work, it's a complex work. I try to define more or less what are the tasks that were performed to obtain the list of multiple stars inside the 100 parsec in relation to the VO tools. So, for example, we start, and for that, we try to download all the exoplanets present in the two main databases of exoplanets, that is exoplanet.eu and NASA IPAC exoplanet. We join it and try to eliminate the duplicates. After that, we try to identify the host star because the exoplanet databases contain only exoplanets. We try to obtain only the host star. And we identified their names using Topcat in connection, crossing with, making a cross match with Sinbad to obtain the unique name, and also with PCR to connect with Gaia DR3 to obtain all the identifier of Gaia DR3 with the purpose of obtaining all of the parameters. With the star already identified, we connect again with Sinbad and with Gaia DR3 to obtain parallaxes and proper motions. Sometimes, if it was not available in those databases, we try to connect with other catalogs, especially, for example, Hipparcos. It's true that the accuracy of the parallax of Hipparcos is not so good. It's not as good as in Gaia DR3, but it's okay when when the parallax were not available in Gaia DR3. All the stars of which distance is more than 100 parsecs are rejected because we are not interested in the stars further than 100 parsec. So with the closer stars, we obtain our sample of start sample, the sample to start to work. We searched for this sample for companions. For obtain the companions, we searched for the possible stars in Gaia DR3. They are sharing with some margins of error the parallax and the proper motion. and also with another database that is very useful for us, that is Washington Noble Star Catalog, that is probably the most official database for binary stars. And finally, we searched about the new information present into the available literature. Finally, if we all of those stars from the sample that are finally single, that has no companions, were rejected because we were not interested in single stars. We are looking for stars that belong to multiple stars. Sometimes these stars, they have companions, but probably they are part of open clusters or movement groups. If they are part of open clusters, we check it in this year with the different databases of open cluster if they are part of open cluster. If they were part of open cluster, we compiled a list of them because in the future we can be used, but not interesting for us in this work. If they are not part of open cluster, we try to find out if the planet that is proposed by the exoplanet.eu or the NASA IPAC exoplanet is not really a planet, because probably the planet is too big, is in between, for example, 13 Jupiter mass, or that can be a brown dwarf, or more, 75, 80 Jupiter mass, that can be an ultra cool dwarf. So if finally there was only a planet and it is a ultra cool dwarf, we don't consider us, because for us they are multiple systems, yes, but they don't have planets. So we collected a list with the ultra cool dwarf systems, but not interested in the final sample or the final list of multiple stars with planets. The remaining stars from the sample, we consider that there were multiple systems and the processes ended. Okay, so as you can see, this complex protocol, a complex procedure to obtain the multiple system, and we use it extensively the virtual observatory tools. As conclusion about multiplicity, we found 215 exoplanet host stars divided in different 212 different multiple star systems. We discovered up to 17 new stellar companions, and we found a multiplicity fraction of 21.6%. That is in line with other results obtained by former studies, but we think it's a little bit low, because even though our sample is very complete, we think that it's not very complete when we speak about late spectral times. I mean L, T, and Y stars. Here in the picture, you can see only some subtypes of multiple stars, the most close to each other. In yellow, you can see the solar system. The black dots represent planets. So solar system is from Mercury to Neptune, to more or less to see the distances, the separations, and the rest, the most close systems. We can see in green, for example, there are circumbinary planets. As you can see, the two stars are closer than the planet that is orbiting each other, orbiting around the two stars. This is the case of circumbinary planets. It's a planet orbiting around two stars at the same time. They are identified about 16, 17 circumbinary systems, and always with two stars. Probably there can exist circuntrinary planets, but we don't know yet any type of these systems. In any case, inside the radius that we mark it as the maximum of 100 parsec, there are only two systems: the RR right? And Kepler 16. Another conclusions, we tried through Bayesian method to obtain what is the relationship between the separation of the main stars and the centricity of the orbit of the planets. If we try to relate the graph of the left side, we can see that the separation has not or decrease a little bit, or the centricity decrease a little bit as the separation of the stars increases. But if you see the gray area, that are the error margins, at the beginning it decreases, after it increases, so it's not clear. So we don't see any clear relationship between the separation of the stars and the centricity of the planets. It's not the case in the right side of the graph, where we are comparing the ratio between the separation of the star and the semi-major axis of the orbit of the planets. That is clearly decreasing, not only the absolute data, but also the green area, that is the margin, the error margins. So it is very clear that as the ratio separation semi-major axis increases, sorry, the eccentricity of the planet decrease. The orbit are more circular. We tried to make another type of studies, statistical studies. We saw or discovered that the average number of planets, one can think that can be bigger in single stars or than in multiple star system, but what we observed that is very similar. There are no significant differences. Contrary is the tendency to have high mass planets that is more frequent in close orbits in multiple systems than in single stars. So in this case, it was more clear. Okay, as future work for this type of studies is to try to use larger sample studies. Now we are limited with the detection of Gaia DR3. DR3 is very accurate. We told that probably is not really complete with the late spectral types, when the stars are smaller. So with, for example, Gaia DR4, we can obtain more accuracy, and we will be able to detect more stars that now are not entering into our work sample. It's, I think that is mandatory to go on studying the multiplicity in stellar system with planets, because it provides, this type of studies provide us a lot of information about stars, about planets. We need to increase the detection in weaker companions, as I say, probably with Gaia DR3 or with better observations or more accurate observations. It could be necessary to increase the characterization of nearby stars. This point, we already started to work on that. In fact, the last paper included in my PhD is an article that has sent to Astronomy and Astrophysics, currently is under supervision review. That is the characterization of all multiple systems inside a radius of 10 parsecs. So very close to the sun. We should understand better the stability of wide and fragile systems, because we discovered that there are systems that are at the verge of to be broken, this gravitationally bound, probably due to the low gravitational bound, and of course due to the tidal disruption forces in the galaxy. We can search for all spectral types, not only the biggest star. We can make a deeper study about hierarchical system. I put here a future work that can be the teleanalysis of HD 1416 system, because we discovered that it can be part of an open cluster that has not yet studied. So it can be the origin of a new open cluster known for the astrophysical community. Also, we should study the multiplicity of stars inside dense areas or open clusters. The list we collected about the ultra-cool dwarfs companion maybe could be a great idea to understand better, improve the statistical significance of the results, because we saw, for example, with the number of planets, it was not really significant with the available data. Also, it could be nice to simulate planetary formation, probably not our team, but other teams that are more used to work with simulations to try to perform this simulation, and also to compare with systems with planets, because for the time being, we didn't compare these multiple systems without planets. So it could be a good future work. Okay, to finish my seminar, I want to describe my PhD thesis. The title is Multiplicity of Stellar Systems in the Solar Neighborhood, Wide Binaries, and Planet Host Stars. My supervisors that unfortunately has not been able to be present here, that are Dr. Caballero and Dr. Cortés, that probably they are now connected through Teams. Dr. Caballero from Centro de Astrobiología in Villafranca del Castillo. Dr. Cortés from professor in Universidad Complutense de Madrid, and ex-postdoc also in Centro de Astrobiología. My thesis defensory date would be by mid-June, if there are no problems. If there are critical problems, maybe it will be deleted or postponed to September, but I'm at the verge to obtain my PhD thesis PhD in astrophysics. Included papers 5, 3 published in astronomy and astrophysics, 1 in monthly notices, and the 5th one, the work that I described before, the description of the stars inside the 10 parsec is under referee review in astronomy and astrophysics. And that's all from my part. Thank you very much.
Awesome.
Thank you.
The environment is around so we have any questions from the group? Please raise your hand. And Javier, I'll ask one of the questions, because the people on Zoom can't hear us. So when people ask questions,
I'll repeat the question. Okay.
If there's any questions, raise your hand.
For the presentation, I was wondering, have you got the orbits of the planets? Are they the same orbits as the multiple stars? So are they all orbiting the same plane, or are they in some?
Okay, the question is in multiple system if the planets are orbiting in the same plane or in different planes, right? Yeah. Okay, we didn't study the orbits. We tried to use only the eccentricity when it was available, or the distance, the semi-major axis of the planet. But we are not trying to to obtain the data about where are they orbiting, if they are orbiting in the same plane or not. It is important, especially when for the detection method, because it depending on how is the plane of the orbit, you can detect in a way or in another way. But it was not the target of our study, so we didn't know exactly what is the plane of the orbit of the planets. Thank you.
Any more questions? Almost on the side. Typically, you want to tell us almost all of the stage. Okay, so I'll ask a question. So the multiplicity diffraction that you quoted, for that was for the stars within 100 parsecs. Actually, so it was 30%. So what? I guess it's a sort of multiple part question, so what is that multiplicity diffraction of? Is that the multiplicity diffraction of multiple stars with planets, or is that just simply the multiplicity diffraction?
No. The multiplicity fraction is only for multiplicity stars with planets. Yes. We didn't take into account that when I was describing the process in the sample, when we detected a single star, we left apart from the sample, so they are not studied. We only focused the multiplicity fraction on stars with planets exclusively.
So I guess the next question is, how complete is the planet search for stars within 100 parsecs? I really have no feel at all.
Okay, we don't know exactly. Normally there is. I repeat the question. It's okay. Okay. I repeat the question.
Please.
Yes. Okay. Okay. The question is. Sorry. It was about it. Sorry.
How complete is the
yes.
planets detected around the moon?
Yes. The question is about how complete is the sample of planets orbiting around multiple systems. The answer is that we don't know exactly because there is also some observational relation, because not all the stars are observed depending on the spectral type to obtain the data. So there are probably stars that has not been observed. So it's not really complete. So we are very aware or very proud, you can say, that about the completeness of the sample of stars, but we are not aware, not really sure about the completeness of the planets, the detected planets. So I think the detection of stars, of course, is much easier than the detection of planets. So we know that the completeness is not very high in terms of planets.
Do you sort of consider that sort of 30% as a kind of lower limit of the multiple systems that host planets? So would that be fair to consider it like that?
The question is about there is a low number of or low bound or low limit about the number of planets for stars, but we didn't evaluate that. We only took the available data without evaluating about how complete is the sample. It's true that this sample will be increased when we detect that there are new stars with planets, new multiple stars with planets, because as we saw in the procedure, we discarded all the multiple systems without planets, but the number of discovered planets is increasing a lot in the last years. So probably in 2, 3, 4 years, we'll have more information about new planets that should be included into the sample to be studied.
Is there any further questions in the room? Unfortunately, we can't really field questions on Zoom unless people write in the chat. Yes, but I assume there's nothing in the chat. So in which case, I'd like to thank Javier again, and yeah, thanks to you all for your patience as well for that unfortunate delay. So thank you very much, Javier.
My pleasure.